Well, thank you for sticking around. Thanks to the organizers for inviting me. I want to talk to you a little about the kind of work that we've been doing at the University of Wisconsin. Primarily an area called quantitative ultrasound, and how we're relating or attempting to relate that to the underlying structure of tissue. We have two main applications that drive this work. One is improving breast ultrasound, primarily for breast cancer diagnosis. Recent studies have demonstrated that ultrasound is really quite sensitive. A combination of ultrasound and mammography is really very sensitive, but it leads to a rather high biopsy rate, with a large fraction of those biopsies being benign tissue. And so if you can increase the specificity of breast ultrasound, you can greatly improve on that. The other large application that we're involved in is trying to quantitatively assess the uterine cervix in pregnancy, because early softening of the cervix is a major cause of preterm birth, and that has substantial implications, as I'll speak to in a minute. We all know breast cancer is a big deal. Statistics are up there. Imaging is not sufficient, so biopsy is still the gold standard. But there's also the problem that clinicians are hindered to some extent in their ability to convey information back and forth, because they rely largely on so-called expert interpretation of images. So one of the net goals of this also is hopefully to help improve in that communication. And the statistics of preterm birth are rather stunning. About 1,400 babies are born in the U.S. every year prematurely, about 1 in 8. About 13 of those die per day at an early death. There's about a 75-fold increase in the risk of early death as a result of being born preterm. And lots of things cascade from the fact that the baby's not fully developed at the point of birth. And so it's really a devastating problem. And again, clinicians have little ability to communicate. This is an example of that challenge, though. If you're a radiologist, the challenge is you see this breast ultrasound image, and you have to describe to the patient and to other physicians what you see. And so the kinds of things that they use are to say how bright are the echo signals here compared to surrounding fat tissue, and how well does ultrasound propagate through it compared to surrounding tissue. So how hypoechoic or hypoechoic or isoechoic is it, and does it shadow or does it enhance? Meaning, does it attenuate the tissue of the acoustic wave more than the surrounding tissue, or does it allow better propagation? This one would be described as hypoechoic and shadow. But in that description, there's nothing that says how hypoechoic it is or how much does it shadow. We can do better than that. So to try and improve on this communication problem, the radiologists have come up with a set of descriptors called BI-RADS. BI-RADS descriptors for both mammography and then separately for ultrasound. But you can see from this that there are a lot of descriptors that are describing the morphology of the tumor, but there's also descriptors that describe echo patterns I mentioned before and the posterior features. So if we focus for a moment on the echo pattern, we see that the description of a hypoechoic lesion is really very prevalent, which is really no surprise, because if it's isoechoic, it's going to be pretty hard to see. There's not many that are hypoechoic, more scattering in the surrounding tissue. A lot of tumors are actually hypoechoic, but only about 40% malignancy when you see that feature. So by itself, it raises suspicion, but not enough to act on that alone. A lot of benign tumors are also hypoechoic. So again, this tumor is described as hypoechoic and shadowing, but we'd like to remove some of that subjectivity, actually quantitatively measure those parameters. We'd also like to provide information that's not available in standard remote imaging, and as Tom mentioned, elasticity imaging is one of the ways to do that. This is a phantom being scanned with ultrasound, and you can see in the B-mode image there's really little or no evidence that there's anything abnormal about that field. But when you perform elasticity imaging, the fact that there's a spherical inclusion is clear. So what can we do to provide information that's not otherwise available to the clinician? Well, all this fits well into the context of a large-scale effort that's being led by the Radiological Society of North America called the Quantitative Imaging Biomarker Alliance. It's an alliance between the radiology community, pharma, industry, the manufacturers, the federal government, FDA, NIST, funding agencies, and clinicians and academics. And the basic idea is to convert imaging systems with expert readers into measurement systems. So the idea is the system then will provide some objective measure of a quantity and report that. And then the effort of this Quantitative Imaging Biomarker Alliance, or QIBA, is to create protocols that describe how you obtain that information in a standardized way, and then profiles that describe what that information will tell you. What can you do with that once you get it? In the manufacturer's realm, it allows them to provide a QIBA-compliant device that if you follow the procedures, you should get measurements within some specified range for particular disease processes. And that should help in diagnosis and conveying information to other physicians. So how do we approach this problem? Well, we approach it from a basic linear systems model. The idea is that you're trying to obtain information about soft tissue properties, and you're approaching that with an imaging system. But in obtaining that information, the properties of these two systems is convolved to give you some raw information available. And as I'll demonstrate in a minute, ultrasound systems do, in terms of signal processing, horrible things to the signal to try and reduce the information content to something simple for display. I illustrate that here, where we have the echo signal amplitude, the radio frequency echo signal amplitude is a function of time. And you can see it's, if you know anything about signal, it's an RF signal. An ultrasound system calculates the envelope of that signal. Basically hits the peaks and valleys. And then it decimates the content of that, subsampling that very coarsely. And the amplitude of the green dots as a function of time is encoded into the brightness on the screen as a function of time and space. And that's a B-mode image, a brightness mode image. So in this process, basically an ultrasound imaging system is throwing away a lot of information. And our approach to this is to retain that information and use it to estimate parameters that hopefully are descriptive of underlying processes. So we know from Lord Rayleigh, 150 years ago or more, that the limiting conditions are pretty well described. When the object is relatively large compared to the wavelength, we get behavior like specular reflection, Snell's law. When the object is small compared to the wavelength of the ultrasound, then we have what we call Rayleigh scattering, and the echo signal is proportional to the 4th power of frequency, the 6th power of the major dimension of the object. But there's not a lot more that's available about the details of that scattering structure. Physics is far more interesting in between those limiting conditions. And so we're generally operating in the realm where the size of the particle is on the order of close to the wavelength of the acoustic sound, the acoustic wave. And so we're going to try and use models to help us extract physically descriptive parameters of how that wave is propagating that help us describe the underlying properties of the tissue. And we call that area of investigation quantitative ultrasound. So what kind of characteristics are we interested in? Well, one of them is echo signal coherence, because one of the typical things that's assumed when you develop signal processing strategies to estimate these parameters is that you have incoherent echo signals. There's a lot of advantages to the assumptions that things are isotropic, homogeneous, and basically tiny compared to the wavelength, but that doesn't always apply. And so echo signal coherence can become important. We also look for anisotropy in acoustic wave propagation properties, things like sound speed attenuation, scattering properties, because they can indicate the presence of an aligned or elongated structure. We also look for inhomogeneity because we want to estimate average properties typically, and any inhomogeneity is going to cause us to increase variance in estimates. And we look for nonlinearity in some of these parameters, in particular, as I'll get to in a moment, the viscoelastic properties of tissues. So the kinds of properties that we're measuring then are measures of echo signal coherence. What are the things that might be causing coherence? Backscatter coefficients, which are a fundamental material property, just like mass density is of a material. And then we can derive a number of parameters from the backscatter coefficients that indicate various properties of the underlying medium. Attenuation coefficients tell us how quickly the wave energy is being lost. Sound speed, and then as I mentioned, the viscoelastic properties, as Tom mentioned, from various approaches of elastography. So there's a number of properties that we can estimate from this. We're not advocating discarding the B-mode image because the morphology of the tissue as seen in the B-mode image is typically quite valuable, but there's a number of things that we can do, and I'll talk briefly about these backscatter and attenuation coefficients. The basic concept of our approach, though, is analogous to MRI. A B-mode image is a lot like a proton density image in MR. If you throw away all the things that you can do in manipulating how you acquire an MR image, you basically get an image of the MR signal strength, and that's like an ultrasound B-mode image. But you can manipulate how you get that data to get T1 weighted images, T2 weighted images, diffusion tensor imaging, functional MR. We're doing the same kind of thing, but it's really a much more difficult problem with quantitative ultrasound. Quantitative ultrasound has actually been around as long as medical ultrasound itself. But an easy explanation for one of the reasons this is so much more difficult a problem is that if you're an MR physicist or an MR engineer, you can write down a diagram in a standard way of drawing pulse sequences. That anybody else that does this could view that pulse sequence and understand what you're doing. You can't do that with ultrasound because there are so many free parameters in how we do what we do that it's just not simple enough to write down a simple drawing of what's going on. You can draw schematics, but they take a lot of explanation to have any sufficient detail. So if we want to estimate a parameter, how do we approach the problem? Well, we use an inverse approach, and that requires a model. How do we model what's going on and compare that model to our data? So we need a model for something. Well, we go back to our standard image here, and we talk about that BI-RADS parameter of the acoustic echo pattern. And this one is hypoechoic, but we want to measure how hypoechoic. So we're going to use a backscatter coefficient for that. Backscatter coefficient, as I mentioned, is a quantitative measure of how much something scatters. And so how do we estimate it? How do we measure it? How do we model it? Well, with very few assumptions, we can write down an equation for the scattered pressure. And we can relate that directly to the backscatter coefficient. And so don't worry about the content of the equations, only the fact that from first principles, we can write down an equation for what's going on. And then compare our data to that model and see how well our data fits the model. Does the model predict what we think is going on? We can write down models for isolated scatterers. We can write down models for scattering from a continuously varying impedance distribution, which largely is more applicable to tissue. And then we can compare our data to that model. So here's an example where we have a phantom that has glass beads. We know the properties of all the constituent materials. We can calculate from first principles what the scattering properties of that phantom should be. We can compare our backscatter coefficient measurements to that model and see that over a couple orders of magnitude we have very good agreement. But this is from our lab from a little over 20 years ago. Can other labs do that? Well, in collaboration with folks at University of Illinois, Mike Woolsey and friends, we got together at their lab with some phantoms that we made, some animal models that they had developed, and did cross-platform measurements from rather low-end systems, midline systems, and high-end systems, all measuring backscatter coefficients on a phantom for which we knew scattering properties really well. And we get really very good agreement in backscatter coefficients across a fairly wide range of frequencies and a wide level of sophistication in systems. Doing the same kind of thing, except measuring attenuation in an animal model, for a couple of different animals that have rather different frequency dependence of attenuation, again, we get fairly good agreement in attenuation across these platforms and over a wide range of frequencies. Applying this to in vivo breast data from our lab, I realized after I put this together that I grabbed the wrong plot. But it's the same parameters, but I have more data. With 3 parameters, separating all fibroadenomas in our data set from all cancers in our data set, we get a 100% accuracy in this, and trust me, I don't expect that that's going to hold up. But this classifier, this Bayesian classifier, is under-trained and under-tested. It's not as bad as it looks here. We have about 19 per class here, so it's closer to minimally trained. But nevertheless, this sort of approach appears to have a lot of promise, and so we continue to pursue that. I want to go back to this idea and say again, a lot of parameters. We've been using motion tracking for a long time to look at blood flow. We heard about that this morning. We can also do elasticity imaging, as Tom mentioned, and go to the physician and something gets poked on. Lots of typical examples. The basic strategy, though, as Tom was suggesting, is something called speckle tracking. And the idea is you line 2 signals up pre and post deformation at some point later, they don't line up so well. And so the idea is, how far would I have to shift one line to make it match up to the other compared to the distance or time away from where it is lined up? And that's an engineering description of strain, or relative deformation. So this is basically what the imaging systems are doing. The idea is that you use generally a phase-sensitive detection system, imaging system, either MR or ultrasound, I have my bias, acquire a map of anatomy, deform the tissue slightly from any of a number of different ways, and then track the motion after deformation. Get another map of anatomy and track the deformation between those two, and then from that deformation field, extract information about viscoelasticity. So here is 2 ultrasound fields from a phantom before and after deformation. Look at a line of data down the middle of it, plot one relative to the other. You can see one looks like it's shifted relative to the other, but the shift is actually depth dependent, it's strained. Track motion along little pieces of segments of that data. Plot the displacement as a function of depth. You can see that the displacement follows a fairly straight line for a while, changes slope, and then changes again. Do this same tracking strategy everywhere, you get this image. And this again is that data. Just a simple phantom with a spherical inclusion. But applying that to breast tissue, one of the kinds of things that you can get, remember our favorite image, this is another one like it, where you can't see where the back of the tumor is. If somebody asks you how big is that tumor, you don't really know because you can't see the back side of it. Do a strain image on that, and now you have a much better idea what the tumor boundaries are. If you wanted to biopsy, you could say where might be the appropriate place to biopsy, where you don't want to biopsy. One of the other things that we learned, though, is that as you deform the tissue and track motion through the deformation, contrast in strain images changes. We understand that by thinking about the stress-strain relationship of various tissues. This is out of Rob Howe's lab, Paris Wallman's thesis, showing stress-strain relationships for benchtop measurements of various breast tissue types, showing that the small strain shear modulus, the slope at low strains, varies a small amount among most tissues. A couple of them have considerably higher small strain shear modulus, but the curvature of these appears rather unique. So, working with friends at Boston University, Paul Barboni and Assad Oberoi at Rensselaer, they have methods for estimating the small strain shear modulus and that nonlinearity parameter from this data. And so that looks like a very promising approach to try and add more quantitative measures to describe tissue. This is images from a 2D CMUT. I stuck that in for the benefit of the talks yesterday. This is a prototype transducer that Siemens had at one time that looked very promising, and hoping that that was going to market. We did some elasticity imaging and the linear modulus inversions on that, and it really looked promising. So I wanted to talk also about the idea of relating this to the underlying tissue structure, and this is an example, a couple of examples. One of the approaches that we started using a few years ago was in collaboration with the folks at University of Illinois, where they were taking serial slices of tissue, doing standard histology processing, assigning tissue type to the various pieces of that tissue, assigning acoustic properties to each of those tissue slices, and then reassembling those slices into a volume of the acoustic impedance distribution, and then trying to relate that to the underlying scattering properties. We took a different approach in Kansas using multi-photon imaging technique. We heard a little about this yesterday, called second harmonic generation. The advantage of this is that it's a direct image of collagen. Collagen is one of the few tissue types that responds in a particular frequency range to this sort of multi-photon approach. And we're looking at a cross-sectional slice of a cervix here that is about 15 millimeters in radius and top to bottom about 55 millimeters, but it's data acquired at 1 micron resolution. And looking at subregions of interest here, where you don't really see, or potentially don't see, much alignment, when you blow this up, the alignment becomes much more clear. And our approach is to try and relate objective measures of collagen alignment and organization here to that underlying impedance distribution function from the continuous impedance distribution model, where this is the correlation coefficient, or the correlation function for the underlying impedance differences that got us to a backscatter coefficient. We can relate that directly to the correlation function that we get from these imaging systems and try and get a direct one-to-one relationship. We're rather early into that game, but that's basically the strategy. The other thing that I wanted to address is another approach, as Tom mentioned, to estimating elastic properties of tissues is the idea of inducing shear waves with acoustic radiation force. We're doing that in the cervix to estimate how stiff the cervix is. Basic communication among clinicians is how soft is the cervix. Cervix softening too early is a matter of concern for them, but it's a subjective measure. How soft is soft? Measure objectively the shear wave speeds, which are directly related in simple models to a shear modulus. In the cervix, that's not so simple, but the shear wave speed is still proportional to stiffness. And what I wanted to show here is that there's underlying biological variability as you measure along the length of the cervix. These are hysterectomy samples that were unripened versus those that were ripened with misoprostol, a standard drug that's used in gynecological procedures to soften the cervix, to do things like insert an IUD, for example. Give a small dose of that, and in these hysterectomy specimens, we could see a substantial change in how stiff they were. But there still was the underlying biological variability, and we need to account for that if we want to go into the clinic and make reproducible measurements. And we've recently done that in a study in the labor and delivery clinic, where these are women that the baby has progressed to term, but they're not delivering. So they go to labor and delivery, where they try and induce labor. One of the things they try and do is soften the cervix, so it's soft enough for the baby to pass through. The question is, has it softened enough for the baby to pass through? Cervix starts out with nominally a 5 millimeter canal that a baby has to go through. So the cervix has to soften a lot to expand out enough to get a baby's shoulders through. The question is, how soft is soft? Well, even in third trimester, where the cervix has already softened a great deal, we can still, in labor and delivery, measure a large difference between pre and post softening in those third trimester softened cervices, if we account for that underlying biological variability. So here's examples of where we're overlying some of that data, these quantitative measures from ultrasound, onto these SHG images. These again are cervical images. These are longitudinal slices, so again about 15 millimeters in height. Again about 55 millimeters or so in length on these. It's difficult to make the assessment from these images, but again you need to blow things up to that higher spatial resolution to see the underlying alignment that is consistent with what we call an excess backscattered power loss, a parameter I haven't described at all here, but it's one of those parameters that we use to indicate the presence of an aligned structure, and also maps of coherence, one measure of coherence. So skip through that and jump to the conclusions. Basically, inverse problem approach has been around for a long time in this sort of realm, and a lot of the parameters we're describing have been around for a long time, but we've made progress in how you estimate those parameters. We've made progress in understanding things like biological variability. Forward problem analysis is appearing to be really quite useful. We've been at it for a long time in simple phantoms, but using that approach for tissues looks like it really has merit. But it's largely driven by improvements in systems also, where transducer frequencies, where 15 years ago breast ultrasound transducers may have been 5 to 7.5 megahertz, now they're 10 to 15 megahertz. That increase in frequency gives us increases in contrast, increases in spatial resolution, broader absolute bandwidth, increased signal to noise in these systems. 2D arrays are huge in this realm, but also understanding the underlying biological variability is really key to advancing the field. It was really a deterrent to this sort of work 20 years ago. I want to acknowledge a great many people that have helped us over the years, and NIH in particular for funding our work, and thank you for your attention.
The service looks like it would be superly nonlinear in terms of its elastic properties. Is that true?
Well, we're doing shear wave methods, so without any preload, we're trying to avoid nonlinearities. In talking to Marie Mueller at IEEE this year, Marie had acquired a bunch of data and had not been controlling for that, and she was using the standard transvaginal probe. And to get that probe into place, you have to push on the cervix a fair amount, and her data was all over the place. Some of it really very stiff, and she agreed it was probably from preload. And when she learned to not apply as much pressure, she's stabilizing how much preload she's applying, but she's still applying preload. So she's likely to have different results from ours. But yeah, nonlinearity is probably going to be a problem. We're doing it the way we do it for a number of reasons, and nonlinearity is one of them.
I have an attenuation question for you.
Sure.
So, do you expect to see power law attenuation for any of these shear wave measurements? I was asking
Well,
about day
you
this
know,
summer. What do you expect to see them?
I might defer to Tom because Tom's got some of that in his book, but I would say that there are some efforts to try and estimate shear wave attenuation from these propagating shear waves, but it's a far more difficult problem than it is for compressional waves because these waves are diffracting and you can't see that diffraction or much evidence of it because you're only doing 2D tracking in a 3D propagation. And there is dispersion going on also. So there are a couple of competing things that would confound any measurement. So people are attempting to do that. I have a lot more hope in objective measures of dispersion than I do in objective measures of attenuation, but I'm not giving up on that either.
So for the orientation of fibers from the SHG images, using any algorithms to trying to get quantitative numbers of colors to fibers?
Yeah. We got started using curvelet analysis. Curvelets are a special kind of wavelet analysis that is designed for this sort of task. And that seemed to be going quite well, but there are variants, and just straight up wavelet analysis appears to have promise also. So although we are trying to do objective analysis instead of subjective analysis, we're not married to any approach yet because we're not convinced which is best. So we continue to investigate that. Any question?
So, correcting for attenuation, back to coefficients, is that over, is it figured out now?
I'm not sure that I'd go as far as to say that we have an ultimate solution. I think that has been a hindrance for many years, and we have a very viable solution that I have a fair amount of confidence in. We continue to do tests in progressively more challenging phantoms, simple layered phantoms, which with previous techniques would simply fail. We do a very good job on. So with multiple layers, either of varying the backscatter, which has been a real problem, or varying the attenuation in a continuous attenuation field. We can account for either of those really quite accurately, but we still want to continue to test it.